Hello. So this video is devoted to the idea of linear model, how we interpret linear models, and what are the assumptions behind it. So in order to understand this, please consider the idea of conditional mean used on this table. So this example is purely hypothetical. It's not about real life data. It's just to demonstrate you how we calculate conditional mean. So please imagine that there are 5 possible values of capital per worker stock: 100, 200, 300, 400, and 500. Let's express it in terms of US dollars. So for different countries, those levels of capital per worker stock correspond to different values of income per capita. So let's say countries with 100 capital per worker stock have this, and this level of income. Several countries with $200 worth of capital per worker stock have those levels of per capita income, where one value corresponds to one country, and so on and so forth. So, of course, we can calculate the general mean for the entire sample, or in our case population. We assume it to be population. I'll explain the difference in a moment. So you will get this value, 3,150 US dollars and 76 cents. However, this is not what we are interested in. We want to see how capital per worker stock determines the value of income per capita. So in order to do this, we have to calculate the mean of income per capita for each level of capital per worker stock. So if you calculate the average value for all the countries with capital per worker stock worth of $100, this is what you have. This is conditional mean. What value of income per capita you should expect if the country has $100 capital per worker stock? The same applies here. You take all the countries with capital per worker stock of 200 and you calculate the average value. So this is your new conditional mean. What value of income per capita you should expect if the value of capital per worker stock is equal to 200, and so on and so forth. So it's easy to notice that when the value of capital per worker stock increases, conditional mean increases as well. To be more precise, here you can see this relationship. So for each increase in capital per worker stock, we observe increase in expected income per capita level. So this is exactly the idea of conditional mean. So this is something you should expect if you have no information about the value of capital per worker stock in the country. This is the average value of income per capita for all of those countries. However, if you have information about capital per worker stock, then you discuss the idea of conditional mean. So what value of income per capita you expect, depending on the value of capital per worker stock. And you can see this function is increasing, although it's not exactly linear, but you can definitely see that this is something similar to linear trend. Because, there were some approximations, and those are not real life data, and we assume some, ideal, truly representative sample here, which is not true because this is a hypothetical example. So this is something to represent the idea of linear regression. We already discussed this last time during the last video, but I just wanted to provide more solid theory for you. So this is the value of conditional mean. You interpret this in the following way. What is the expected value of y depending on the value of x? So if you know the particular value of x. So as you remember, beta 0 stands for the value of intercept. So this is a very standard notation of a linear function. So to be more precise, it represents the value of income per capita if capital per worker stock is equal to 0, because at this point x is indeed equal to 0. But of course you can put any variables here. I just wanted to stick to the previous example. And beta 1 stands for the slope of regression line. So basically it's delta independent variable, conditional mean of y, divided by delta in independent variable. So this distance divided by this distance. And it will stand for beta 1. By the way, in our case, it's definitely less than 1, but it's not uniform. So beta 1 can be smaller than 1, can be bigger than 1, it can be positive, it can be negative. This is just some, particular example. So please don't be afraid if you see a decreasing function in your regression model output. Like, it all depends on assumptions. Like in our case, of course, higher level of capital is expected to result in higher level of income, because this is something natural, yes? If country has more resources, it's expected to be more wealthy. It's expected to be wealthier. But of course, if you put, for instance, crime rate or something different, that would be rather a negative relationship between income per capita and this variable. So it all depends on variables you use in order to estimate regression. Okay, so what does it mean to discuss linear regression? So in our case, we will discuss linearity in terms of parameters. I will explain. So linearity in terms of independent variable means that independent variable is a linear term. So there is a linear relationship between the dependent and independent variable, like this one. So this relationship can be perfectly described by a linear function. So this is linearity in terms of variables. And linearity in terms of parameters means that coefficients are linear. So for instance, this is linear regression, both in terms of variables and parameters. So you see that x is linear, beta 0 is linear, and beta 1 is linear as well. So this is regression which is non-linear in terms of variables, because we have x to the power of 2 as the independent variable, but still linear in terms of parameters, because beta 0 and beta 1 are both linear terms. By the way, I have no idea why I also mentioned beta 0, because it's constant, so please concentrate only on beta 1. And finally, this one is nonlinear regression, neither in terms of variables, neither in terms of parameters, because you have beta 1 to the power of 2 and x independent variable to the power of 2 as well. So during this course, we will concentrate on this one and this one. So we will discuss regressions which are nonlinear in terms of variables, but still linear in terms of parameters. Okay. So basically, linearity in terms of variables implies that the rate of change of the dependent variable is constant. So we have a constant slope. As you remember, slope can be calculated as delta dependent variable divided by delta independent variable. And in our case, this slope will not depend on the value of independent variable. It's constant. So whether you analyze relatively small values of x or relatively big values, it will be the same. It does not change. But of course, linearity is very restrictive assumptions. for many variables, the relationship cannot be described by a linear trend. You will need something different. Again, we will discuss this later, but please keep in mind that usually non-linearity is justified either by the nature of data or some economic theory. I will provide an example. So this is estimation where GDP per capita is taken as dependent variable and capital per worker is taken as independent variable. So this is our regression line, and as you remember, those red crosses stand for empirical observations. So let's say like this pair of values. So there is a country with this level of capital per worker and this level of income per capita, and we just put it on the graph. So this is a production function from Solow model, where A stands for technological coefficient, K stands for the stock of physical capital, and L stands for the stock of labor, and its underlying assumption that alpha takes the value between 0 and 1. So this is something resulting from diminishing marginal product of labor and diminishing marginal product of capital. Each additional unit of capital is less and less powerful in terms of increasing output if we assume that the stock of labor is the same. And the same, by the way, will apply to labor. So that's why alpha is smaller than 1, yet positive. So since this is the function with constant returns to scale, we can do this trick, divide both sides by stock of labor. In this model, we assume that stock of labor is constant, and this is what we get at the result, where Y stands for per capita income, our dependent variable, and small k stands for per capita stock of capital, our independent variable. And again, it's to the power of alpha, which means that this function is increasing, but it's not a linear function. It's actually concave function. So it means that instead of going like this, being described by the linear trend, the relationship between those variables is described rather by this function. You see? So this is how this function should look like according to economic theory. Not a linear function, but a concave function, which again results from this equation. So actually it was a mistake to run this regression as a linear model in terms of variables. It's not linear. It's not like this. It should be rather like this. But again, you're free to do whatever you want with the data. Like, program will not tell you that you are wrong or this trend is not linear. It's up to you to analyze it. So I already have the first reason, not to use linear regression model, but to assume this shape of regression line. So the next thing is about data. So you can see that if you analyze only shape resulting from those red crosses, it's more similar to the concave function I depicted here rather than a linear model. So as you can see, both data and economic theory tell me that linear model is not a good choice. It shall be rather non-linear. Okay, so when we talk about misspecification, the error term provides key information about correct specification of the model. I will explain. So you remember that this is the expected value of y depending on the value of x. So this is conditional mean. Yi stands for actual empirical observation. So basically, if you take this model and you stick to this level of capital per worker, so for this level of capital per worker, this is the expected value of income per capita. So this is the conditional mean. However, this would be the actual value, what we observe in reality. Because this regression line, of course, cannot fit all the data. It can just select the best linear representation. So again, when you take empirical observation and what you expect for this level of capital according to your regression model, the distance between those two values stands for the error term. So again, error term is the difference between empirical value of dependent variable and expected value of dependent variable. So this is how you can specify it. This is just some kind of rearrangement when you take the empirical value of variable as the sum of expected value and the error term, which of course can be both positive and negative. If you put this expression instead of the expected value of y from the previous equation we analyzed here, so you just put this one instead of this one in this model, this is what you have. So of course, in perfect ideal world, all the regression models are 100% correct and error terms are equal to 0. However, this is not something we can observe in reality. So in perfect world, the value of the error term conditional to the value of x is equal to 0. In our case, it's positive. And this is a normal thing, yeah? This is not a mistake. Like, even if you select the best variables, the best model, and do your best, you will still not avoid those non-zero error terms. This is something normal. So actually, there are several reasons for this. Sometimes your theory is not good enough. Like, in our case, my theory told me that this regression line is not linear. Instead, I specified a linear regression line, which is my bad. Sometimes even theory is wrong. Sometimes data are not available, which results in those errors. Sometimes the variables are intrinsically random, and there is nothing you can do about this. So there is still some portion of variation which cannot be explained by the model. Sometimes you choose poor proxy variables. We will discuss this a bit later, but in general, proxy variable is a numerical variable you use in order to denote something which does not have perfect numerical representation. For instance, human capital is a purely theoretical concept. So this is something economists use in order to explain stock of skills, knowledge, and talents in the economy. It's assumed to affect economic growth rate, the level of development, and so on. But honestly, there is no perfect way to calculate human capital. Like, you can take, for instance, average years of schooling, which is a popular way. You can take different education enrollment rates, like secondary, tertiary, and so on. You can use amount of money spent on education in the economy, and so on. So all of those variables will in some way describe human capital, but neither of them is perfect. So this is the idea. Sometimes you just cannot select proxy variables which are good enough, and that's why you end up with those error terms. So yeah, there are many reasons. You cannot avoid this. So regardless of what you do in order to avoid this, you will still have some error terms in your model. But what you can do is to minimize it. So it's something not avoidable, yet possible to mitigate. So later we will discuss what you can do, in order to select the best model, and how you can use different types of statistics in order to understand whether your model is good enough or not good enough. But as for today, it's more than enough. So thanks a lot, and I hope you enjoyed this video.